Hello, this video will be a little bit different. I'm gonna try to explain a whole topic about capacitance, and I'm gonna talk about capacitors, I'm gonna talk about capacitance, I'm gonna talk about dielectrics, I'm gonna talk about circuits, and it's gonna be a little bit slower, perhaps, but I will try to cover all the topics. So, what is a capacitor? I'm gonna try to start with the types of circuits, and then I'm gonna try to explain how the capacitors work inside that circuits. So we basically have two types of circuits. We got parallel and series. So in the small summary I just made for this topic, I was trying to compare the capacitor, like a circuit, and the capacitors to a bank. So imagine that you have a street, and in that street you have a lot of money flowing. It's like money, 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 money. And just in the middle of that street, you put a bank. Before that, the money flowed normally and without a problem. And now with that bank over there, you have the entrance that's over here and the output that's over there. Out. And at the beginning, the bank had zero cash. But as the time started going through, then the money started like concentrating in there until the bank is full. When the bank is full, then you have the same amount of money here and the same amount of money there, and then the money just starts flowing again towards the second part of the street. First part, second part, bank. Okay, that's simple. And then imagine that the bank is now the capacitor and the money is the voltage. So there's a wire over here, and then you have small gap of the wire, and you have a continuous wire. So the charge, or well, the electricity charge will flow first from a battery. Oh well, that's important too. The electricity always travels from the less potential to the most potential. No, from the most potential to the less potential. So if I have a lot of money in my right hand, I will try to put it in the left hand that has no money, so I can balance it. So this is my less potential, this is my most potential, and it will try to flow from here over here, and then try to continue over here until it gets to the negative side of the battery. And as it hits this part, you get this positive and this negative. And so we've got here a circuit. You can see this is the battery that is sending electricity to a wire, and eventually there's a gap, and we have here the first type of capacitor, that is the parallel plate capacitor. So imagine this is the wires, and eventually you hit a wall, and that wall has a determined area, two equal areas that are parallel, two plates, and then the charge start to accumulate here, and it's trying to go towards the second plate, and there's a gap here that right now we're gonna assume that it's an empty space, so it's vacuum. And once this plate is completely charged, then the electrons will try to go through the air, well, through the vacuum, towards the second plate. And once the second plate is completely filled, then we will have here an electric potential difference that is equal to the electric potential difference on the battery. Electric potential difference meaning voltage. So I hope that I'm not being that's a lot of topics over there, but we're basically talking about a bank where you got some money in the street and there's only one place that stores that money. Everything else is just flowing around, and so the amount of money in the street is basically the amount of money in the bank, because it's the only place where it's being stored. So now we got that. We got that if we only have one capacitor and we have one battery, you basically have that the same, well, once the capacitor is full, you have the same amount of voltage in that capacitor than you have in the battery. It's basically the same thing. They both store energy. They both have the same amount of energy going from positive to negative. And before, I was talking about parallel and in series. So what happens if we locate more banks in our street? Okay, there's first we had one bank only, and now we have two in the same street. This is the street, and well, each one has a different type of ability to store energy, money. So this ability to store things is the capacitance. So capacitors have capacitance, and capacitance is the ability of a capacitor to store energy and charge, to electric potential and charge. And here, the thing is that if we take all of this and we try to analyze how the sum of those capacitance relate to the total capacitance of the system, we got an equation that is like this. The equivalent capacitance is equal to 1 over the equivalent capacitance, and that's equal to the capacitance of the first capacitor plus the capacitance of the second capacitor. So that's the way it behaves. And if we were trying to understand, here, what's the thing that it's always the same? Well, as they're different and they have different abilities to storage energy, obviously the voltage will be different, because it's okay, I'm voltage and I'm going through the street and I leave some voltage behind, so now I have less voltage. I went to the first bank and I paid something and I continue walking, and I find another bank and I pay a little bit more, and then I have no more money left. because I paid everything that I had from the battery. Yes, I hope this relationship analogy is it's working. It worked for me. I hope it will work for you. So, while the voltage it will be different in both of them. Will normally be different if they have different capacitance, but it will definitely be different to the voltage of the battery because it will be separating into two different paths. But the amount of charge that it's going through them, it's always the same. Why? Because even though the voltage is staying in every path, the relationship, I have it over here, I have it. Well, the voltage, it will be the sum of the voltages in, as I mentioned before. And the charge will always be the same. That's important. And then, if we talk about capacitors in parallel, we will be talking about two different streets. So, here we have C1, here we have C2, and well, now what we will have always the same is, you can see over here, is the voltage. Voltage of C1 it's equal to the voltage of C2. The thing that will be changing now is the charge. The amount of charge that it will be distributed over here will be Q equals C1 times the voltage. And that's Q1. And Q total will be C1 plus C2 times the voltage of the system. And all those are the relationships of the two different types of circuits. And how do you find the equivalent capacitance? Is the sum of both capacitors. As you can see here, I'm only using two capacitors, but you could use like any type you want, like any number if you want, and it will still be the same. This relationship is, well, it doesn't matter how many capacitors you have, it will always maintain the same. Okay, so we've stated the two different types of circuits that you can have: parallel and in series. In the series one, the thing that it will always remain the same is the charge, and in the parallel one, the thing that will always remain the same is the voltage. That's simple. Now, if we will try to explain the different type of capacitors, we have three principal ones, and I'm gonna try to explain it simple. We have, as we mentioned before, we have a parallel plate. So yeah, imagine something like that. You can just, well, I'm gonna try to use different objects. We got first two parallel like that, and one is charged, the other one is not, and then this energy over here is trying to go towards this one. And the equation for that one, that's P, parallel plates. The equations for that one is that the capacitance is equal to epsilon naught. Epsilon 0 is, and this will be a concept that I'm gonna explain a little bit more later on, but that's the permittivity in vacuum, all right, and that's a constant. That will be times the area over the distance between the plates, and that's the area of the plates, obviously. So we can see that if we increase the distance, the capacitance decreases, and if we increase the area, the capacitance will increase, and so on, so on, so on. So the area is directly proportional to the capacitance, and the distance between the plates, it's inversely proportional to the capacitance. Everything okay over there? So that equation comes from analyzing the electric field inside the plates, but we will try to not explain that part because it's a little bit complex. So now I'm gonna show you another type of capacitor. This other type of capacitor is the cylindrical. So it's something like that. Yeah, you can see it. And this type of capacitor, imagine that you have a positive outside and then a negative inside. It's positive and then no, forget it. It's the other way around. You got a positive cylinder inside and a negative big cylinder outside, and you're trying to analyze the electric field over there. So you will try to make a Gaussian surveys and try to see how the electric field behaves. And once you do all of that, you will find out that the capacitance in a cylindrical, it's equal to it's epsilon naught 2 pi times the length over the logarithm of the division b over a. 1 V and A are the radius of each of the cylinders. And well, that's another important equation. And then the other, like the last type of capacitor is the spherical. That it will be something like that, like that's a sphere. And in that type of capacitor, we get that the capacitance it's equal to 4 pi epsilon naught times A B over B minus A. So remember, these equations come from the electric fields particular to each surface, and we'll not try to explain that part. The important thing is that depending on each surface, we have a different capacitance, and this capacitance as we explained before, is the ability of a surface or a space to accumulate electric charge, voltage, electric charge and voltage. And so let's go back to the bank, and we will try to think of the capacitance, like the ability of the bank to storage money, just like that. And a thing about the capacitors is that, unlike to the bank, in the capacitors you can add something that will enable you to storage more money. So like if you have a physical space over here and I'm trying to like put some boxes up to like full of cash over here and it's full. But in the capacitance, as we're working about with little things, you can use something called dielectrics. Dielectrics modify the electric field, enables the capacitor to storage more energy. And so this epsilon naught here will change. This epsilon naught is the epsilon naught for vacuum, and you will normally use something that is called dielectric permittivity. Dielectric permittivity is epsilon naught times K, and K, I'll write it bigger. In this case, K is the dielectric constant of each material. So imagine that there's this gap, and we'll go back to a parallel plate because it's the simplest ones. There's this gap, and this is full of energy. And then I place something that is naturally an insulator inside that gap, and that gap will increase the maximum voltage that it can be stored over there. So depending on the material, that the K changes. For example, we before did a problem about the electric charge in the heart of a fish, and we were observing that fishes are able to identify electric charges. For example, sharks are able to identify electric charges in the sea because the electric charge in water travels easily. That means that it's a dielectric permittivity, or the permittivity on water, it enables electricity to flow easily than in air. I think that's pretty clear. And what I need to explain. I think that'll be it. Basically, another equation that I missed is that the capacitance, it's equal to the charge over the voltage, and that's the voltage from terminals A to B, and I guess that's it. I hope that's it, and I'll be answering questions in the comments of this video. Thank you very much, and